Hello, I am Santos, and today I'll be going over proprioception and the way carbohydrates are utilized by our body and the two pathways that process can take. To begin with proprioception, what proprioception is the information that our brains receive to about our muscular dynamics. What that means in basic terms is where our muscles are shaped, sorry, not how shaped, but how our muscles are in space based on how tense they are and how lengthened they are. The receptors that provide this information to our spinal cord and brain are called proprioceptors. These are modified muscle fibers called muscle spindles, and what they do is that as they run parallel to our regular muscle fibers. So when the muscle is stretched, they are also stretched. What that does is that it'll send a sensory neuron, or it'll trigger a sensory neuron in order to tell our brains to bring it closer or farther. Commonly, what's mentioned when talking about proprioception is the knee-jerk reflex. And as mentioned before, with a muscle spindle deformation is what leads to the contraction, or it leads to a reflective contraction. So in terms of the knee flex reaction, the when when force is applied to the patellar tendon, the tendon in the knee, it briefly stretches out the muscle spindles within the tendon. That will send a signal through the sensory neurons to notify to contract quickly. That quick contraction kicks our leg forward, and the relaxation after the muscle spindles have shortened during the brief time the leg has bent forward will return the knee back to will relax to now let the knee fall back into place. So that knee-jerk reaction is the response to the brief stretch that the patellar tendon face was faced with, to now return back to its normal length. To wrap up about proprioception is that proprioception is the information we get from our sensitive protoreceptors to by how stretched or how deformed the muscle is, to relate back to us where the muscle is in space and how flexed we are. This is done mostly subconsciously, so we don't have to dedicate any conscious thought to feeling where we are at all times. What this means in the actual practical sense, that if I was to hold my hand behind my head, I myself would be able to know how many fingers I hold up by knowing which fingers are flexed and which ones are stretched. This lets me know and how much tension is under just due to gravity itself. My joints is all sent back to my spinal cord, which goes back to my brain, to let me know how many fingers, such as 2 right now. That's a basic explanation of what proprioception and the knee-jerk reflex is. Now to begin on the two paths the carbohydrates can take. Now, as we talk about ways that our bodies are able to metabolize, I have a chart here that we'll use later. As our bodies are able to metabolize carbohydrates, there are two main pathways. There is the anaerobic and the aerobic. The aerobic pathway is those are the two big ones. The aerobic pathway is highly effective at making the energy for the amount of glucose it uses. For a glucose, it will yield about 30 to 32 ATP. This is very efficient, as when there is oxygen available, you're able to yield much more energy for especially long-term activities. This can be anything from a long walk to a long run, a jog, a long hike, a long rest, or even long sleep, as we have oxygen readily available and able to have the time to digest and metabolize our oxygen intake, we're able to disperse it to efficiently use the aerobic process. The way it works is that the glucose is then taken through after glycolysis is taken through the Krebs cycle, and then the electron transport chain to yield such high amounts of ATP. Now, the other pathway is the anaerobic pathway. The anaerobic pathway is also has a great job. However, this great job is done to quickly produce energy. The quickly produced energy is great for an explosive lift, or to exert greater force quickly over a lift, or activities that last past 10 minutes, or sorry, 10 seconds to 2 minutes, where you are able to use the energy already lacking oxygen. Where there is no time to take oxygen, our bodies will mostly use this anaerobic pathway, as the lack of oxygen will still require us to still has a requirement for energy to complete the activity. This will be great for, as mentioned earlier, sprints, for resistance training, and for just explosive movements such as large jumps too. While it is great for these explosive movements, there is the drawback of it being much less efficient. It will sacrifice efficiency for the sake of readiness, for the sake of urgency. To signify how greatly the difference is, the aerobic pathway can yield to 30 to 32 ATP, while the anaerobic pathway can only yield up to about 2 ATPs for the glucose used. Now, while not a energy pathway, for not a carbohydrate pathway, there is another system that we'll be using for our model here, called the ATP-PC system. What this is, in summary, is just the energy that's already within the ATP that's already within the muscle cell. Now, what this can be used for is activities that can last up to 10 seconds. This energy system is always present for every physical activity that we do. However, if an activity goes past this 10-second mark, you will be incorporating the anaerobic systems. This will be done for a jump or a very, very fast sprint, again, lasting less than 10 seconds, such as 100-meter dash, as we'll get back into, as well as just beginning of any movement. Now, to begin with our diagram to explain how this relates to the world of sports, I have drawn up this triangle with aerobic here on top at this top point, and anaerobic here at this point, and the ATP system here at this point. To take use of 3 sports, we're going to use the 100-meter sprint, the soccer goalie, and then the soccer midfielder. To begin with the 100-meter sprint, I will place the 100-meter sprint right here between the ATP-PC system and the anaerobic system. As the activity will last slightly over 10 seconds, you will incorporate the anaerobic system to create that brief amount of extra energy. However, since your body has very, very little time after activity is complete, after completely is started, to use oxygen, there is absolutely no aerobic capacity to actually take and use the oxygen that we have. However, we'll be using most of the glucose that is in, and the ATP that is in our muscle cells already. It's brief, it's explosive, which is why it's the perfect pathway to exemplify the ATP-PC system, as well as slight of the anaerobic system, especially if you're a slower runner. Now the other, excuse me. Now the other sports, as mentioned, the soccer midfielder will fall mostly right here in the slightly more towards the peak of the aerobic system. this the soccer midfielder is not going to stop. Is not going to stop and start most of the game. They're going to be constantly running throughout the entire 45 half, or if they are really good, the entire game itself. Now, because of this high energy demand and long duration, it will be using mostly aerobic capacity, especially once they reach their their they're able to take in more oxygen to meet their demands needed. Now they also are playing for a long time, which allows the oxygen to be actually used for most of the game. Now I do include slightly aerobic, anaerobic activities such as kicking or longer exchanges with the ball, but it will very much lean towards the peak of aerobic. Now the goalkeeper will be right here. I would argue more so right here. I would argue it's because the goalkeeper is going to be hanging out. I say colloquially, the goalkeeper is going to be in a much steadier state than all the other players, as they're going to be more stationary throughout the entire game. However, there are exchanges where the ATP, in fact, I could even argue that it could be right here. Now, I say that because there are, again, they're going to be more stationary than all the other players for the large duration of the game. However, there's going to be brief exchanges where they'll be using the muscle, their energy that's already within the muscle, and even longer exchanges when the ball's on their side of the goal. In anaerobic capacity, when they go up, down, left, right, defending multiple kicks from the opposing players. Now these are three great sports to really explain the uses of energy, especially, like I said, the goalkeeper, as they're stationary for most of the time, very explosive for one or two kicks, and then if the exchange goes much longer, they're going to be more so right here towards the anaerobic because of the constant exchange. So to recite one more time, aerobic being the use of oxygen that we have time to metabolize and adequately, efficiently use to make more energy for long, steady state sports and activities. The ATPPC, which is the energy that's already within our excuse me, already within our muscles, and the anaerobic, the energy that we use that we can quickly create at the cost of lack of efficiency for prolonged intense activities such as lifting, sprinting, that lasts longer than 10 seconds but less than 2 minutes. This one all the way up to 10 seconds, and again, always active at the start of movements and especially active during explosive movements. Now, all these systems is never a direct, you can never be fully aerobic, you can never be fully on the ATPPP system, and you can never be fully anaerobic. However, determined on the intensity and the duration of your activity, you'll start leaning to more, your body will have a bias towards any one of these energy systems. Thank you. Again, this is Santos talking for UTSA, the Strength and Conditioning course for the summer semester. Thank you.